Good evening, everyone, and welcome back to our live coverage of another Rocket Lab Electron mission from Rocket Lab Launch Complex 1, Mahia, New Zealand. We are awaiting for the 49th Electron liftoff at 3 p.m. New Zealand Standard Time. For NASA's second PREFIRE launch on a mission named PREFIRE and ICE. Today's mission will launch last one of the two 6U CubeSat spacecraft in a different 525 kilometers altitude from the previous PREFIRE launch on a near-polar sun-synchronous orbit. This launch marks Rocket Lab's amazing 49th overall launch and 7th mission of this year. Hello, my name is Dipta Maitra, performing the commentary for today's mission launch. We are super excited bringing you the coverage of Rocket Lab's PREFIRE and ICE mission, dedicated second mission launch for NASA's PREFIRE CubeSats. PREFIRE was jointly developed by NASA and University of Wisconsin-Madison and is managed by the agency's Jet Propulsion Laboratory in Southern California. Now, before getting into mission details, just a reminder, the Boeing Starliner crew flight test is aiming for tomorrow, that is June 1st at 12:25 p.m. Eastern Daytime, that is 16:25 hours UTC, with backup dates on June 2nd, 5th and 6th respectively. For now, weather is expected to be 90% favorable, with ground winds and the cumulus cloud rule being a primary but a little concern only. So far, Rocket Lab reports the weather is looking good for today's Electron launch opportunity and the range is ready to support. We hope that they are able to launch on time and not have to push too far. Rocket Lab is currently targeting a liftoff time of Electron from Mahia, New Zealand at 11 p.m. Eastern Time, 8 p.m. Pacific Time on Friday, which will be 3 p.m. New Zealand Standard Time and 3 a.m. UTC on Saturday, that is June 1st. Firstly, we would like to thank all of you for joining us for today's launch and would request that if you haven't already, please like the video to help YouTube's algorithm bring in more space fans and rocket enthusiasts. Also, it will be so kind of you subscribing to our channel.
Check out our website for open roles right now across additive manufacturing, vehicle integration, test site operations, and more.
As you can see, the strong back retraction has started. Also, we would like to welcome Fairmade back again. Thanks for tuning in, and sorry that time I couldn't respond you in a hurry. I am also doing good, but not so good, you can say. Again, staying awake at night, late nights, what to do.
Today's mission profile includes all of the usual launch milestones you've come to expect from Electron. At T-minus 2 seconds to liftoff, Electron's 9 Rutherford engines on
Electron
the
that's
first
supporting
stage
today's
will
mission
light up
is an
to power the
orbital
rocket
class
for
reusable
flight. The
three-stage
launch pad's
rocket
hold-down
which is
mechanisms will
18
be
meters
released,
tall.
and Electron will begin its ascent right on T0. From there, Electron reaches supersonic speeds in under a minute, and we'll hear that as a call out from Mission Control just before we approach a mission milestone called Max Q, or Maximum Aerodynamic Pressure. Now, once through Max Q, Electron's Rutherford engines will continue firing hot for another minute and 20 seconds or so before their scheduled shutdown at MECO, or Main Engine Cutoff. 3 seconds later, the first stage will separate from the second stage, and Electron's first stage will fall away while its second stage will light up its sole Rutherford engine to carry on with the mission. Up next will be the separation of Electron's nose cone, about 30 seconds after stage 2 engine startup. Meanwhile, the stage will be continuing cruising along for another couple of minutes before the next mission milestone, a battery hot swap. Now, that's a maneuver that is unique to Electron, which I'll explain more about when we reach it during the flight. After battery hot swap comes the second stage's final actions, shutdown of its engine before the second stage separates from the kick stage, which is what is carrying NASA's PREFIRE satellite. And then within an hour of all of that happening, we will come up to the moment for payload deployment that ends the mission for Electron, but which marks the start of operations on orbit for the NASA PREFIRE mission. All of that is coming up shortly now that we are just under 5 minutes until liftoff for PREFIRE and ICE. It's time to send it over to Mission Control to take it from here for the remainder of the count, and I'll be back with you shortly after liftoff. So go NASA, go PREFIRE, and go Electron.
Stage LD mission code.
LD stage.
Please prepare the stage 1 and stage 2 for LOX top up. That's Victor 5000 and Victor 5100.
So where I was
LOX top up
left behind,
work.
that
PLS LD and mission code.
LD PLS.
Please resume the LOX top up. That's Romeo 7600 Bravo.
Resuming LOX.
Electron that's supporting today's mission is a orbital class reusable 3-stage rocket
GC LD mission
compared to SpaceX 2-stage rocket, which is 18 meters tall and 1.2 meters wide. An orbital launch vehicle designed specifically to place small satellites of up to 300 kilograms, that is 660 pounds, into a wide range of low Earth orbits. Every aspect of the Electron has been designed for frequency and reliability to meet the evolving needs of government and commercial small satellite operators.
Copy.
And Vicon LD mission code.
LD Vicon.
Please shift the auto sequence to T-minus 12 minute hold. That's Golf 2400 for you.
Copy that, in work.
Now we are in a hold.
So from comms there from Mission Control, it sounds like we are recycling the clock back to T-minus 12 minutes in the count, and we're standing by for more information.
LD stage on mission code.
Stage LD.
Sequence 69, the stage terminal board check sequence is complete.
Copy, thank you.
This optional hold point provides a safe recycle point before we enter the terminal count. Now today's mission, PREFIRE and ICE, is the second of the two back-to-back Electron launches for NASA's PREFIRE mission. PREFIRE stands for Polar Radiant Energy in Far Infrared Experiment. PREFIRE CubeSats is tasked with measuring heat loss from both the Arctic and Antarctica in an aim to help researchers better understand Earth's energy budget. The duo 6U CubeSat spacecraft in two different 525 km altitude near polar sun-synchronous orbits, that is with an inclination of 97.5 degrees, each with a heritage miniatured infrared spectrometer covering 3 to 54 micrometers of wavelength region at approximately 0.84 micrometer spectral sampling, operating for about one seasonal cycle, about a year, with diurnal subsampling.
As you might notice, the clock is held at T-minus 4 minutes and 45 seconds. That's a hold in our launch operations. And a hold can happen for any number of reasons at any point up to the release of the vehicle hold down clamps. So what we're doing now is standing by publishes a new T0.
The second satellite will be deployed to the same 525 kilometers circular Earth orbit on a similar but different trajectory to the first satellite, so that both can crisscross each other every few hours near the poles. It's along these orbital paths that PREFIRE will measure the heat loss to the space from Earth's polar regions in form of infrared radiation. The data will help to improve climate and ice models and provide better predictions of how the planet's sea levels and weathers are likely to change in the future. Each satellite is fit with specially shaped mirrors and detectors for splitting and measuring infrared light, and will make its reading using a device called thermocouple, similar to sensors found in household thermostats. PREFIRE will supply scientists with new data on a range of climate variables, including atmospheric temperatures, space surface properties, water vapor, and clouds. Changes at Earth's pole can influence global weather patterns and affect sea level rise. The climate data collected by PREFIRE will help to produce a more accurate read of the future of some of Earth's coldest, most remote regions, and in turn the future of our planet. Also, it is worth mentioning that the payload is supplied with a canisterized satellite dispenser that both CubeSats will deploy from once in orbit. While these musics are going on in background, let me just talk about the Electron a little bit in details. So on the top, it's the payload fairing, or you can say Electron's fairing. Electron's payload fairing protects the payload from encapsulation through flight. The fairing is 2.5 meters tall and 1.2 meters wide, and the fairing separation occurs usually using pneumatic unlocking with using springs. It can deliver 200 kilograms to 550 kilometers on sun-synchronous orbit. Electron's payload fairing is a composite split clamshell design and includes environmental control for the payload. During separation, each half of the fairing is designed to rotate in a hinge away from the payload, resulting in a safe separation motion. Expanded and tailored fairing options are also available depending on customer's need. Rocket Lab's Kickstage offers our customers unmatched flexibility for orbital deployment. The Kickstage is a third stage of the Electron launch vehicle used to circularize and raise orbit to deploy payloads to unique and precise orbital destinations. The Kickstage is powered by Rocket Lab's in-house designed and built Curie engine. In its simplest form, the Kickstage serves as in-space propulsion to deploy payloads to orbit. At its most advanced configuration, that the Kickstage becomes Photon, Rocket Lab's satellite bus that supports several year duration missions to low Earth orbit, mid-Earth orbit, lunar and interplanetary destinations. The Rocket Lab's Kickstage is designed to deliver small satellites to precise and unique orbits, whether flying as dedicated or rideshare on Electron. So coming up on the Kickstage, what it requires, the requirements of Kickstage. The Kickstage enable missions that require deployment of payloads at multiple planes with multiple inclinations, including constellations. Then we have higher altitude deployment. In that case also, Kickstage is needed. Coming up, inclination out of range of the launch vehicle or hosted payload support or multiple trajectory changes or sustained low altitude orbits or in case of deorbiting. In all these cases, Kickstage are required and to be used. The Kickstage is a streamlined path to orbit that eliminates the added risk, complexity and cost of having to develop own spacecraft propulsion or using a third-party space tug to deliver spacecraft to the desired orbit when flying to a rideshare. For missions that require extended payload support on orbit or for missions exceeding 2000 kilometers to mid-Earth orbit, lunar or interplanetary destinations, Rocket Lab offers the Photon spacecraft bus, a high-performance evolution of Kickstage. Now below that we have the second stage, Electron's second stage, that it consists of a single vacuum optimized Rutherford engine and linerless common bulkhead tanks for LOX and kerosene. It is a little bit resembling with SpaceX design. With an expanded nozzle, Electron's second stage engine produces a thrust of 5,800 pounds of thrust and has a specific impulse of 343 seconds. The 1.2 meter diameter second stage has approximately 2000 kilograms of propellant on board. The Electron stage 2 has a burn time of approximately 5 minutes with a Rutherford vacuum engine as it places the kick stage into orbit. High voltage batteries provides power to the LOX, that is the liquid oxygen, and kerosene pumps for the high pressure combustion, while a pressurant system is used to provide enough pump inlet pressure to safely operate. During the second stage burn, two high voltage batteries takes over for the remainder of the second stage burn. Upon depletion, the first two high voltage batteries are jettisoned from the Electron to reduce mass and increase performance in flight. The engine thrust is directed with electromechanical thrust vector actuators in two axes. Roll control is provided via a cold gas reaction control system also. Now below the second stage, we are having our first stage. Electron's first stage consists of 9 sea-level Rutherford engines, linearless common bulkhead tank for liquid oxygen and rocket grade, that is RP1 kerosene, and an interstage. Rocket Lab's flagship engine, the 5,600 pounds, or you can say 24 kilonewton producing thrust Rutherford engine, is an electric pumped LOX or kerosene engine specifically designed for Electron launch vehicle. Rutherford adopts.
For those of you just joining us, we are currently in a hold for today's Electron launch, but we have 20 minutes remaining in this launch window. So let's sit with Mission Control for an update.
We still have 20 minutes for this launch window to end for today. So coming up where I was left behind, that Rutherford engines adopts an entirely new electric propulsion cycle, making use of brushless DC electric motors and high performance lithium polymer batteries to drive its propellant pumps. This cuts down on much of the complex turbomechanically what is happening turbo machinery typically required for gas generator cycle engines, meaning that the Rutherford is simpler to build than a traditional engine but can achieve 90% of efficiency. Rutherford is also the first oxygen or hydrocarbon engine to use additive manufacturing for all primary components, including the regeneratively cooled thrust chamber, injector pumps, and main propellant valves. The stage 1 and stage 2 Rutherford engines are identical. It's just the same as in case of SpaceX Merlin engines, here with an exception of a larger expansion ratio nozzle for stage 2 for improved performance in near vacuum conditions for Rutherford engine. All aspects of the Rutherford engines are completely designed in-house and are manufactured directly at Long Beach headquarters in California, USA.
You likely just heard there from our launch director in Mission Control that we have set a new liftoff target time of 15:46 local time, which means the team has now recycled and will go into a new go, no-go poll at the T-minus 12-minute mark. So we'll sit here and wait for that update from Mission Control on that go.
And to all operators, LD and mission code, we are proceeding now with the go no-go sequence. Stage.
Stages go.
Avionics.
Avionics is go.
GNC.
GNC's go.
Recon.
Recons go.
T1.
T1 is go.
GC.
GC is go.
PLS.
PLS is go.
RSO.
RSO is go.
MET.
MET is go.
RF.
RF is go.
MN. LD sub. LD sub. LD mission code.
LD sub is go.
Copy, thank you. The go-no-go sequence is complete. We are T-minus 10 minutes and 57 seconds in counting. We go for the terminal count order sequence at T-minus 10 minutes. From this time, the freebird hold procedure is in effect.
Good news there from Mission Control. The clock has been recycled and all stations are go for launch. And we are at T-minus 10 minutes, 29 seconds and counting with a liftoff time set for 15:46 local time.
With sequence 55, the paired terminal check sequence.
Understood. Sequence 55 in work. Stage 1 igniter pressures verified. Hydraulic pressures verified. LD-GC on mission cord.
GCLD.
LD, the pad terminal checks are complete.
Copy, thank you. Avionics LD mission code.
LD avionics.
Please proceed with sequence 56, the avionics terminal check sequence.
Copy. S-band switch to high power for flight.
Stage LD mission code.
LD stage.
Proceed with sequence 57, the stage terminal check sequence.
Understood, sequence 57 in work.
Stage 1 and 2 high voltage batteries ready for flight.
GCLD mission code.
LD-GC.
Please proceed with sequence 58, launch pad ready.
Understood, sequence 58 in work.
LD avionics mission.
Avionics LD.
Sequence 56 complete.
Copy, thank you.
All engine blips nominal. All engines ready. LD stage on mission cord.
Stage LD.
Stage terminal check sequence, sequence 57 complete.
Copy, thank you.
As we can see on our screen, the strong back for Electron is slowly starting to retract ahead of its flight scheduled for 15:46 p.m.
As you saw, the strong back retraction has already started and it has been retracted. Now coming up,
LD-GC on mission cord.
GCLD.
Hold down mechanisms are armed and the strong back is retracted for flight.
Now we will be disabling
Copy,
the
thank
TVC battery charging and switch the flight termination system to internal power. After that, nearly at T-5 minutes, the FTS failsafe is enabled. As you heard, FTS status is green on internal power. T-4 minutes, we will be having AV battery charging being disabled. After that, at T-3 minute and 30 seconds, we will conduct the final range status check. At T-3 minutes,
As we head into T minus 4 minutes in the count, the next major milestone we're listening out for is the start of the auto sequence, where Electron takes over the count all the way down to T0. So we'll hand you over now to Mission Control to take it from here for the remainder of the count, and then we'll be back with you shortly after liftoff.
LD-GC on mission cord.
GCLD.
LD, the ECS is disabled. Pad auto sequence is armed. The pad is ready for launch.
Copy,
I
thank you.
was saying that at T minus 3 minutes, the stage 3 switches to internal power and flight mode is enabled. At T minus 2 minutes and 30 seconds, the vehicle is declared ready and we have the go ahead for auto sequence start. At T minus 2 minutes, the launch auto sequence kicks off and it confirmed the Electron is on internal power. Then coming up at T minus 1 minute and 50 seconds, ground power will be disabled.
To all operators, LD admission code. From now on, there should be no red flags on your critical LCCs. Beacon LD mission code.
LD beacon.
Please lock the auto
At T
sequence
minus
and
1
confirm.
minute,
Auto sequence is locked.
Please confirm all expected primary flight computer ASCOs are green.
Confirmed.
We are go for auto sequence start
so
at
the launch
T minus
director
2
giving
minutes.
go for the launch.
LD is gone for launch.
At T minus 1 minute and 50 seconds, ground power will be disabled as I said earlier. Then at T minus 1 minute and 40 seconds, liquid oxygen tank pressurization begins. At T minus 1 minute and 10 seconds, stage 1 and 2 locks reach flight pressure. We have another hold.
And hold.
To all operators, LD and mission code. We are proceeding now with the LV on paired securization and ECS enable sequence.
We've just heard a hold call from Mission Control there, so now we are listening out to hear what the latest information is for launch ops.
So going through the timeline, as I was saying, that at T minus 1 minute and 5 seconds, fuel tank pressurization occurs. At T minus 57 seconds, the fast purge is enabled. Then at T minus 55 seconds, stage 2 fuel reaches flight pressure.
Interoperators, LD and mission code. At this point, we are proceeding with the preparations for LOX detank. PLS LD mission code.
LD PLS.
Please proceed with the PLS prep and detank sequence.
Copy prepping
Sorry,
with
what
PLS
stage?
detank.
Stage 1.
A final update here from Mission Control that unfortunately, with the remaining time left in the window now exhausted, we will have to wave off for today's launch attempt for NASA PREFIRE. We have plenty more opportunities to launch in the rest of the window though, so keep an eye on our social media channels for an update with a new launch date. This is Rocket Lab Mission Control signing off.
So as for today, the launch is not going to happen. Let's check out their social media websites that what they will be saying about the next launch opportunity. So with that, we will wrap up our coverage for now. Be sure to check out the social media for the new update of new launch dates. We want to thank all of you joining us with today's launch, although the launch didn't happen, and we hope you all enjoy the weekend ahead. Once again, thanks for joining us, showing your such patience, love and understanding, staying till the end. We are glad to have you all here with us. This is AstroYonder Live and me, Dipta, signing off for now, and we will see you next time.